Hello and welcome to this artificial neural networks tutorial. This tutorial is made for beginners who haven't had experience with neural networks, and the purpose of this tutorial is to understand how the neural networks work. So before we get started, if you have any questions, just send me a message or write a comment below. I don't think this is the perfect tutorial, but I think this can be helpful. And if you have questions, it will help me improve the tutorial later on. Alright, so first of all, what are neural networks? Neural networks are a way to estimate functions. So if we have some inputs and we would like to estimate some outputs, we can use neural networks. And for today's exercise, we will estimate the price of an apartment. So the problem we will solve today is we want to sell an apartment. We know the size of the apartment, how many square meters it has, the distance to the city center. If the distance is bigger, we expect the price to be smaller. And the year of construction, if the building is newer, then the price will be higher. So we have these 3 points of data: the area, the distance, and year of construction. These will be our inputs. And we would like to know, how much should I sell the apartment for? How many euros? So we have these 3 inputs and this one output. Also, we will be given a list of apartments. So we know for an apartment of 55 square meters with a distance of 2.7 kilometers from center and year 2008, we have a posting that says it should be sold with 62,000 euros. So we actually have some prices from which we can learn a system that will estimate the price. So this table is also given. So in this tutorial we'll have 7 steps. The first step is to read the prices from the table. The second step is to try out a simple neural network. Then we'll measure the accuracy of our network to see how good it is at estimating the price. Then we'll see how we can improve the accuracy. How can we make the estimator better, closer to the actual prices. Then we'll move on to a more complicated network. And in the end, we'll see how neural networks are implemented in practice. I mean, how can you use them in real scenarios? And the last one will be further resources, so you can learn more about this topic. All right, long way ahead. Let's get started. So first of all, why do we care about apartment prices? I mean, why is this problem even relevant? So this problem isn't what neural networks do. It's just a small example. Just with neural networks you can do many things. This is just a simple example. And the same principles apply to bigger neural networks for more complex problems. So, for example, if we want to predict in an image if there is a stop sign, we can use neural networks. So this can also help driverless cars. In here, we want to estimate the probability of a stop sign to be in an image. And the inputs would be the image itself, the image pixels. Another problem which can be solved with neural networks is estimation. Like in the future, what will happen to some values given the past values and maybe some other inputs. And the list goes on and on. Anything that you want to estimate and you have data for it, I mean, you know both inputs and outputs. For some examples, then you can use the neural networks to automatically learn the relationship between inputs and outputs. All right, before we get started, the first step is to actually download this prices table and put them into a project. You can use any language, any programming language you want. If you know how to read from a file and how to write functions, that's enough. We'll use C++. So first we create a project, then download the data and copy this table into our project. This presentation with all the links can be found in the description below. So enter that link and go ahead and download the data. And regarding CSV files, these tables are just text files with commas between the columns. So if we have 55, 2.7, 2008, if we look at it as a text file, it's 55, 2.7, 2008, and so on. So comma is between columns, and we have an enter return between the rows. CSV stands for comma separated values because we have commas between them. All right, so I'll go ahead and open this and click on download, save file, and I already have a new project. So I'll go ahead and take the download and copy inside my project. So here at project neural nets, we have the file. If you open it with Excel, you should see something like this. The area, distance, year, and price. And if you open it with Notepad or anything else, you would see it as a text file with commas between them. All right, so right after you download this file and put it in your project, also use this starting code. We will use arrays for each column. So you have areas, distances, years, and prices. Here we declare the input file, the prices.csv. we know we have 178 apartments, and here we read from the file the areas, distances, years, and prices. So basically we take what's in the file and put it in our program, in our arrays. So let's grab this code and in your source code file, just put it there and maybe also test that it works. So if you print, I don't know, prices of 0, we would expect it to be this one, 62,000. Let's see. So the first price is 62,000. That's good. All right. So this is just the prerequisite. Download the file. Make sure you can read it from the code. And also a warning before we get started. What we will do right now, you shouldn't do it in practice. It's just for educational purposes. So just wait until the end, because we'll see there how you should use them in practice, because it's easier that way. Trust me. So this is where we begin. What is an artificial neuron? Neural networks are made of neurons, and now we'll see what a neuron is. So here is how a neuron looks like. Each neuron actually is a number, which is called activation. So here, instead of activation, we will have a number. We also have some inputs, x1, x2, up to xn, and also some weights. So each input has a weight. x1 has weight 1, x2 has weight 2, xn has weight n. And finally, we have this plus b, which is called the bias. All the weights and the bias are just constants. We'll see an example soon. And what is important is that this activation is just each input multiplied by its weight, and we make a sum out of them. So it's weight 1 times input 1, weight 2 times input 2, weight n times input n, all added out, and finally we add the bias. Later on, with the more complex neural network, we will add something more, but for now this is enough. So let's take an example. Let's say we have inputs 3, 4, and 2, weights 1, minus 1, and 3, and this bias is 2. Now let's try to apply this formula and see what should be the number inside the neuron. Try to compute it, put a pause here, and come back when you have the result. Alright, so if you compute it, it's 1 times 3 plus minus 1 times 4. So you have minus 4 plus the previous 3, we have minus 1. We have 2 times 3, which is 6. We add to minus 1, we have 5. And if we add b, these two, we will get 7. We'll have 7 in here. So the activation of this neuron is 7. Now, back to our problem, we have area, distance, and year of construction, and we want to estimate the price. In the first example, we will use only one neuron to achieve this. So we will have weight 1 times area plus weight 2 times distance plus weight 3 times year plus b. This will be our formula for the price. It looks quite simple, and it is, but it's a good starting point. So this is our estimator so far. Now remember that the weights and this bias are constants. Don't worry about them, they are just numbers. Now let's try to do an example. So let's say the first weight is 2, the second weight is minus 10, and the third weight is minus 1, and B is 50,000 euros. These are just like randomly, quite randomly. Let's see the result. Put a pause here and try to compute the activation of this neuron, like the estimated price. Alright, so if you try to compute, it's 2 times 50, 100. We have minus 30, so we have 70. And we have minus 2000, so it's 1930. And plus 50,000, well, this will be huge. It will be like almost 50,000. It's actually 48,000 and something. So let's try to implement this neural network in code. We should declare 4 global variables. We'll make them global, it will be easier later on to work with them. So we have the weight 1, 2, weight 2 minus 10, weight 3 minus 1, and B 50,000. Write the function estimate that takes the area, distance, and year as parameters and returns the estimated price for one apartment. And remember, our formula is the price is weight 1 times area plus weight 2 times distance plus weight 3 times year plus b. Also in the main function, print to the console, like cout in C++, the first 3 apartments, area, distance, year, and price, and their estimated selling price. So put a pause right now. We'll do this together when you come back, but try to do it yourself. It will be more helpful this way. All right. So if we go back to our code, we will declare double weight 1, which is 2. We have the weight 2 minus 10, weight 3 minus 1, and the bias 50,000. I just copy and pasted them. And our estimate function has area, distance, and year. And it should just return the first weight times area, the second weight times distance, and the third weight times year plus e. So this is just the formula for one neuron, and that should be it for this task. And finally, in the main function, we should print the first three. So we will do a for from 0 up to 3. It's okay also if you manually print them. So if we do cout areas of I, distance of I, years of I, and price of I, and now let's take care of the estimate. So the estimate is estimate of areas of I, distance of I, and years of I. I think I forgot an S here. Yeah. So you have the area, distance, year, and price, and the estimated price here. Let's see how it works. Oh, okay, this looks really bad. Let's add an end line. So we have, here's them separately. So you have this is the first apartment, and the estimated price is 48,000, and the real price is 62,000. It's not even close. It's really terrible. This one is even worse. We have 140,000 euros, and we estimated 48,000. So it's not even close. And the third one, the same. It's quite a horrible estimator, but this is also because our weights are quite randomly so far. So this is it. This is our first simple neural network. We just use one neuron, which is only multiplications and additions. Now, we saw that the first three apartments aren't too great, but let's see how accurate is it in general. So, how can we measure how good the estimator is? We have the real prices, we have the estimated prices, and let's see how we can define a way to measure the accuracy of the price. And one simple way to measure the accuracy is to try out the difference between the real price and the estimated price. So if the difference between them is low, if it's lower, then it's more accurate. If it's big, it's less accurate. So for this second apartment, our estimated price is really wrong, because the error is also really big. So here we take the real price and subtract from it the estimated price, and also use a modulus, an absolute value, because the estimated price can be bigger than the real price, and in that case it's also bad. We want the estimated price to be as close to the real price as possible. So small error, small difference between those two is good, big error is bad. So here we consider that the error is the difference between the two in modulus. There are also other ways, like the difference squared, and this is called the loss function. If you see this term, loss function is the way you measure the error, the difference between the real thing and the estimated thing. In this tutorial, we'll only use this one, the absolute value of the difference. Alright. And now, as a coding task, we would like to compute the average estimation error. Like, take each apartment and find the error, the difference, and add them up to the sum error variable, which is initially 0. And finally, the average error is the sum of errors divided by n. After that, we'll please change the bias to like 60,000. So we increased the bias. We make all the estimated prices higher. And the question is if the average error, if our estimator is better or worse. So if the error is bigger, it got worse. If it's smaller, it got better. And finally, change the bias back to 50,000. Now, put a pause and try to implement this estimation error, like the average estimation error, in your code. Okay, so if we go here, we take sum of errors, which is initially 0. Take each apartment, so we take an I from 0 up to n. First of all, we'll compute the estimated price, which is estimate of areas of I, distance of I, years of I. We compute the estimated price. Then we compute the estimation error, which is the absolute value. We have the ABS function in C++ of real price, which is prices of I, minus estimated price. And we add this estimation error to our sum error variable. And finally, we print the average error as sum of the errors divided by n, and a new line. So let's see. All right, this is weird. So this basically says that the average error is 218. Something is wrong. One moment, sorry. Oh, here I forgot the addition sign. So we have the sum of errors becomes sum of errors plus the new error. So we want to add the new error to the sum of errors. So now if we try again, we get an average error like really big. So on average, we are wrong by 69,000 euros. Now, if we try to change the bias to 60,000, let's see the average error. Now the average error changed from 69,000 to 60,000. The error is smaller, so our estimator becomes better. Let's change back, and we're ready to go to the next task. All right. So this whole thing was a way to measure how good our estimator is. This was important because now we can try to improve it, to make the error smaller. So the next step is trying the network to improve accuracy. So far our network is inaccurate. It has like a very large estimation error. And that's because our parameters, the weights and the bias, have been randomly chosen. We put like a random formula and it didn't work so well, which is quite expected. Now in this step, we will use the apartment prices, the real prices, to improve the weights and the bias. So we know the real data and we will use it to improve the neuron so it estimates better. And one way to do this is using a method called gradient descent. There are also other options, but most of them rely on this. So this is the core of how to improve the performance of neural networks. Now, gradient descent, we have a big error. So if we plot error, we want to make it smaller. We want to go as low as possible. With gradient descent, you won't get to the best thing ever. You will get to the closest minimum. So this will be our goal right here, to improve the error as much as we can. Gradient descent works by choosing an apartment. You take one apartment, you estimate its price using the current weights, which are initially random. You compute the error as the difference between the real price and the estimated price, and then use this error to improve this W1. In the same way we'll improve W2, W3 and the bias, but let's focus right now on the first weight. So we want to change this weight in order to make the error smaller. Now, what do you think? If we increase this weight, now, right now, we count as like each squared meter of the area increase the estimation by 2 euros. Do you think this weight should be bigger or smaller? Do you think if we increase the weight, will the estimated price be closer to the real price? Like, put a pause and think about it for a second. If you increase this weight, this price will go bigger and then it will be closer to the real price. So the error will be smaller if we increase the weight. So the network will be better. Now, let's see in general, how do we know if we should increase or decrease a parameter? In the following section, we will go into a bit of math, so we see how to improve the neural network. If you don't want this, if you want to skip the math, you can just go to the next section, which contains the formulas we'll come up with in the following section. So the formulas will be on how to update the weights and bias for one apartment. Now, let's take a look. if we want to improve this parameter, the first weight, and we take one apartment, let's see how we can improve it. How to know if we should increase or decrease the parameter. So remember that when we computed the estimated price, this was our formula, and for the estimation error we have this formula. Now we know all of the numbers, we can replace them in the formula. So we know that the first weight is 2, the area is 55, and so on. But for the moment, leave W1 as a variable, as an unknown, because we want to make this estimation error as a function of W1, of the first weight. So the estimation error now depends only on constants and the W1. So here are the formulas. We have the estimation error as a function of W1. This estimation price is just this formula, so imagine this goes in here. So right now, imagine we didn't have this formula, just a general function of the first weight. So if this was the error depending on the first weight, let's see what we can do. We have a general function, we don't care what's behind it. Our current first weight is 2, and we know that the error is about 14,000 for this weight. We know that if we decrease W1, in this example, the error will grow. And if we increase W1, the error will become smaller. So that's an improvement. So in this case, we would like to increase W1. How about in this case? Do we want to increase W1 or decrease W1? Well, in this case, we would like to decrease W1 because we want to make the error smaller. So to answer whether we should increase W1 or decrease W1, we can use derivatives. So if a function is increasing at a point, the derivative is positive. In that case, we should decrease W1. On the other hand, if the function is decreasing, the derivative is negative. So in that case, we want to increase the weight. So if the derivative is positive, we make it smaller. If it's negative, we make it bigger. So a simple way to implement this, so if the derivative is positive, then decrease W1 by a small amount. So if the derivative is positive, decrease. If the derivative is negative, increase. But how can we choose this value? How much should we increase or decrease this W1? If you choose a very small value, then it will take us forever to get to this point. The learning will be really slow. Instead, if we choose a big value like 1, it might just jump around like a crazy dude. So in here, we want a balance. We don't want it to be too small, neither too big. In general, you'll see that you will try different values and see which one works. But before that, there is an observation. So there are two cases. If the slope is large, we can decrease W1 by a bigger value. We can take a big step. If this slope is like very big. But if the slope is small, if it's not that big, then we should take a small step. So in general, we would like the change of W1 to depend on the slope we have. So if the derivative is positive, we don't just decrease by 0.01, we decrease by this amount times the derivative. If the derivative is big, we decrease by a large amount. If it's small, we decrease by a small amount. And the same thing for the other case. So if the derivative is negative, it's decreasing. If it's large, we go by a large amount. If it's small, we go by a small amount. Now remember, if this is negative, we should also put a minus so that it becomes positive. We only care about the magnitude, how big the slope is. We don't care about the sign. All right. And if we see here we have a minus, here we have a minus, which can be moved here. So these two are kind of the same. So we can simplify it into just weight 1 becomes weight 1 minus 0.001 times this derivative. Now, coming back to the issue of how can we choose this number, if it's too small, it will learn slowly. If it's too big, it will bounce. And we will keep it as a variable. Instead of putting 0.01, let's consider it learning rate and give it a small value. And we're gonna play with it, try multiple values until we get a good accuracy. So this is like a trial and error. Try a value, see how it goes. If it's not good enough, try another one. Alright, so here we have a formula that says weight 1 will change by a learning rate, which is a constant, times this derivative. Now, how can we compute derivatives? How can we know what's the derivation of the estimate error? So we have this constant, we know that W1 is 2. We know the estimated price and how we computed it. And the estimation error is the absolute difference between the two. Now, if we want to compute the derivative with respect to W1, which can be also written like this, we can split it in two parts. So we can have this first part, which is the derivative of the error with respect to the estimated price, and the derivative of estimated price with respect to W1. So this way we can compute the derivative in two parts. These are easier to compute. So the derivative of estimation error with respect to estimated price, we have a modulus. We know that If this is positive, then it's itself. If this is negative, it's the opposite. So if the estimation price is smaller than this one is positive, so it remains the same. Otherwise, it's the reverse way. This is like only the estimation error. If we want the derivative with respect to estimation price, we see here that the derivative of the estimation error is -1 if the estimation price is smaller than the real price, and it's +1 otherwise. So in this case, it's +1 if we compute the derivative. This modulus is quite weird to derive, to compute the derivative, but that's how we do it right now. And the second derivative, this one is easier. The estimated price, if we compute the derivative with respect to W1, is just 55, which is the area, because everything else is a constant. Now let's recap. We have, first of all, area, distance, and year, 3 weights, and bias. We compute the estimated price, and then the estimated error as the difference. We can compute the derivative of estimation error with respect to the estimated price, using an if. If this is smaller than this, the derivative is -1, else the derivative is +1. This is the first derivative we need. The second set of derivatives is the derivatives of this with respect to each variable. So you have the derivative with respect to W1, which is area. So everything except W1 is a constant. If we compute the derivative, it's just area. For W2, it's distance. For W3, it's year. And with respect to B, it's just 1, because it's +1B, everything else is constant, that's it. Now, you can combine the two derivatives above. So, the derivative of estimated error with respect to W1 is the product of the two. Estimated error with respect to W2 is to price, then price to W2, and so on. And finally, the way we update our weights. So first we declare a constant, the learning rate, which we will use 0.01, and we will take the W1 and subtract from it the learning rate times this derivative. So for each parameter, for each weight and bias, we decrease it by the learning rate times its derivative. And this way, the error will be smaller. So the next task is to write a function called train step with area, distance, year, and we also need the real price. And the first step will be to compute the estimated price. So this one. Then compute all the partial derivatives. This one, these ones, and these ones. And finally do the update, this part. Now pause the video and try to write the function. Alright, if we go back here, we'll take double train step with area, distance, year, and real price. And the first step was to compute the estimated price. So double estimated price is estimate, we can use this function above, of area, distance, and year. All right. Now let's compute this derivative. So if the estimated price is smaller than the real price, if estimated price is smaller than real price, we have the derivative of error with respect to estimated price to be, so if this is smaller than the real price, it's -1, -1, else the derivative, the same thing, is +1. And we also need to declare it, so double this one. So this is the first derivative. This is for the modulus part. Then we will take these derivatives. So I'll just copy and paste them. Double, double, double. It should look like this. And finally, their combination. So the product of the error with respect to price, and then price with W1. Same for W2, W3, and the bias. So here we computed all the derivatives. Now we only need to update the weights and the bias. We just use the formulas. And here the learning rate is 0.1. So here we compute the derivatives and, update the weights. The next task is to use this train step function. So we take each apartment and give it to this train step, which will improve the parameters. After we take each apartment and improve it, compute the average error again and see if it improved. Let's go ahead and try it. So we take each apartment and call this train step function. prices of I. So with this, we take one apartment and improve the network. And then compute this average error again. I'll just copy paste it even if it's ugly, but it's faster this way. Okay, it didn't work. Let me delete this stuff because we already had a sum error. So we see previously the error was 69,000. Now the error is 62,000. So it got better with a little bit. All right. And the final step, after we take each apartment and update the network, this is only one epoch. One epoch means one pass through our data to improve the parameters. Now let's try to do this more times. So let's try to make 5 epochs, meaning to do it 5 times, which is just adding a for loop. And then look at the average error if our network got better or worse. Also, try with a bigger learning rate and more epochs, and then put the learning rate back to 001 and do even more epochs and see if the network got better or worse. It's quite common to play with the learning rate and the epochs number and see what the error is and choose the best ones. So if we get back here, instead of doing this only once, we will do it like 5 times. Like this. So instead of going through the apartments only once, we go 5 times. And if we check now, the error got even better if we do it more times. Now let's try with a big learning rate, 0.1. And here, let's put 10 epochs. Let's see. Now the error got even worse. So instead of improving them, it made them worse. Now the average error is 369,000. So let's change it back, 0.01. And here on the epochs, try 1000. Let's see. All right, now we're talking more about it. So we started with an error of 69,000 euros, and now we got down to 19,000, which is much better. It's still not great, but it's better. And now let's try with even more epochs. I put another 0. We can see that it doesn't get any better. So this is like the best we can do with this new network. All right. Now let's try a little bit to complicate the network. So our network has one neuron which computes the estimated price as W1 times area plus W2 times distance plus W3 times year plus B. This is a very simple formula, but let's try to complicate it a bit. Let's see what happens if we have 3 neurons. So we have one neuron H1, one neuron H2, and then the price. Remember that each neuron had the formula for each input, it has a weight, and at the end we add the bias. So in our new model, we will take one weight times the area, one weight times the distance, one weight times the year plus B1 for the first neuron, the same for the second neuron, and the same for the final price. This one has only 2 weights because it only has 2 inputs. And this example is like a particular example for the fully connected networks. So usually you would have networks that look like this. We have an input layer, we have an output layer. Here we only have one output. And the ones in the middle are called hidden layers. And it's called fully connected because each neuron from one layer is connected to each neuron from the next layer. But no neuron is connected to a later layer. So only between consecutive layers we have connections. Now let's look a little bit at the formulas. So we have the first weight times the first input plus the second weight times the second input plus the bias. And we know H1 is just this sum, like we had previously. And H2, we can replace it with the weighted sum of these guys. And if we remove the parentheses and multiply with each one and reorganize it a bit, we can see that we can rewrite the formula as something times the area plus something times the distance plus something times the year plus a constant, which is very similar to our previous network, where we also had something times the area, something times the distance, something times the year, plus constant. So the new network is just the same as the previous network, just with more constants. And this is really bad. We want it to be better. So the solution is to add a nonlinear function here to each neuron, so we can't open the parentheses and multiply with each one. So if this sounds scary, don't worry. The nonlinear function is really simple. It's called, one of them is called ReLU. So basically, ReLU is a rectified linear unit. It's a really complicated name for what it does. So it's just something like this. If the number is positive, if the input is positive, then it returns the number itself. If the number is negative, it returns 0. So ReLU of 7.5 would be 7.5. ReLU of minus 7.5 is 0, and ReLU of 0 is 0. And this ReLU is useful because it's really easy to compute. It doesn't involve any difficult computations, and it's also not a linear function. It doesn't have multiplications and additions. So if we want to add ReLU to each neuron, instead of activation being the weighted sum plus b, we just do activation equals ReLU of the weighted sum plus b. And ReLU is, as we talked before, just kind of the modulus, but with 0 if the number is negative. Now, try to see what would be the activation if the first input is 3, the second input is 2, we have these weights and this bias. Considering we also have ReLU. So here we have 3 times 1, which is 3. 2 times minus 2 is minus 4, plus 3 is minus 1, and plus b, it is 1. And if we do ReLU of 1, it's still 1. Activation is 1. What happens if b is 0? What would be the activation? So you have 3 minus 4, it's minus 1. And if we do ReLU of minus 1, we have the second case, so the activation is 0 if b was 0. Now, the new network looks like this. So the first neuron is ReLU of the weighted sum plus b. The second neuron is ReLU of the weighted sum plus b2. And the price is ReLU of weights times inputs plus b3. So now we cannot break the parentheses or do anything. Now the new network is more complicated than the previous one, so it might do better. Now try to create a double ReLU function, a function that implements this formula. Download all the weights, I put them into a paste bin link, and write a function estimate2 that, given an area, distance and year, compute the price using the new network. Pause the video and try to do this yourself. Alright, let's see how it goes. So we'll start with the ReLU function. Let's put it like this. Double x. We have if x is positive, return x, else just return 0. Let's get the coefficients from here. We have, oh, these are many coefficients. All the weights and biases. And now we can write the estimate2 function. In which we compute h1 as the first weight times area plus the second weight times distance plus the third weight times ear plus B1, and also do a ReLU over it. Now let's copy paste this for H2. H2 is using the second set of weights and bias, and the same for the price, which is weight 31 times H1, this one, weight 32 times H2, and the third bias, B3. So now we used the formulas from here. H1 is ReLU of this, H2 is ReLU of these multiplications, and the price is ReLU of this weighted sum. Alright, and finally we can return the price. Now if we go to the main function and compute the error for this new network, just put estimate 2 instead of estimate and see the average for new network. Let's see how big it is. So with the new network we got to the error of 16,000. So if you think that the relationship between the output and the inputs is more complex, you can always add or take back some neurons. So it becomes more complex or less complex depending on your needs. All right. What was presented above was just like a playground. You shouldn't use it in practice. In practice, you don't need to write code for estimating and training networks. You can use libraries such as PyTorch or TensorFlow. There are many other else, but these two are the main ones used today, in research at least. So right now I have an example with PyTorch. You can download the code from here. Let me open it, just 1 second. Here we have PyTorch. This is Python. You don't need to understand everything around here, but it's important that the first step is to read the data. The second step is to define the network. And the third step is to write a training function. This is a function that can read the CSV file into an array, a two-dimensional matrix. Then here I normalize the data because otherwise it wouldn't work. It's not really important right now. You can look over it afterwards. So let's see how you can define the networks in PyTorch. So the first neural network which we did in the lab, the one with only one neuron. To make a network in PyTorch, you can create a new class which extends the torch NN module. It's not really important. And here you need to define that the network only has one layer with 3 inputs and 1 output. So here the 3 if we look, 1 second. If you look here, we have 3 inputs and 1 output. And you need to define a forward function which tells how to compute the price. It's basically our estimate function. And since we already declared that we have a layer here, we can just put the layer of X, which is the apartment input. For the second neural network, we have a similar way. We have here 2 layers. The hidden layer, H1 and H2, has 3 inputs and 2 outputs. Actually, two neurons in this layer. And the output layer, this price, has 2 inputs and 1 neuron, or 1 output. And here in the forward function, where we tell how to estimate, we use ReLU of the hidden layer of the input, and then in the output we also use ReLU. My point here is that this is really short, and this is easier to write than putting an estimate function and manually use the weights and multiply and stuff. This is much shorter. And if you have a big network, you won't be able to write the formulas as we did before. All right. Here we create a network, just instantiate one of the classes. And the nice thing is that if I put here 1 neural net or 3 neural networks, it's going to work the same, because the training part doesn't care about the network itself. It's the same any network you have. You need to define how you want to measure the error. Here we use L1 loss, which is the absolute difference. What we used in the lab, the modulus of real price minus estimated price. Here you choose the algorithm which you use. This is stochastic gradient descent. It's a bit more complex than the gradient descent we did in the lab, but it's kind of the same idea. And finally, we take some epochs. Here we put 100 epochs. Take each apartment. We didn't do this in the lab because this PyTorch works differently. We make 0 every derivative. We compute the estimate price, compute the error, the estimation error, and with this loss.backward function, this is like a magical way to compute every derivative. You don't need to know any math, just put loss.backward and it computes the derivatives. And this optimizer.step uses these derivatives to improve the weights and bias. And if we run it, we can see here I put a print for each epoch to see how good it is after each one. And the loss is around 17,000 euros. You can also download the code and try it yourself after you install Python and PyTorch, but was not the purpose. I just wanted you to see that we have 3 steps: reading the data, define the network, and train. And if you want to try another network, you just change the network definition, which is much simpler than do all the math and find out all the derivatives. All right. So the main takeaway from this tutorial, I would like to be that neural networks can estimate a value that depends on some inputs. So if you have a relationship between output and inputs, neural networks can do it. The neural network is like a fixed formula with inputs and some parameters. So in the first example, the inputs were area, distance, and year, and the parameters were the weights and bias. And the second example is also a formula with the same inputs, but it's computed in a more complicated way. So neural networks are just formulas with some parameters. We need a loss function, which is used to measure the accuracy. The parameters, the weights and the bias, are initially random, and we improve them during training using the data we have. Because we know some real prices, we can make our estimator better. Now, if you want to get more information on neural networks, there are some topics which we didn't talk about, which are data normalization. All of these topics are quite general and you can find a lot of resources online, but if you'd like, I can make some tutorials on them too. So, data normalization is used to convert data, like we have years around 2000, but with data normalization we convert anything in the intervals 0, 1 or -1, 1. Because if all the numbers are kind of in the same interval, the network will train better. The train test split is an idea that you shouldn't use all the data to train the network because it might remember by heart the answers. So it's dangerous to do so. And a better idea is use some of the data for training and the rest of the data to test, to check if it works also on data that it hasn't seen before. And this is to test if the network generalizes well. And you can also read about underfitting and overfitting, two main issues with neural networks. And also batching, which is the concept of doing multiple inputs at the same time. So if we process together multiple apartments, it will become faster. Okay, I really like these resources. So the first one is a visual tool. So here you can play around with neural networks. It's from TensorFlow. Basically the task is you have some points in the plane. Here you can choose 4 variants. And the task of the network is to classify, to guess if one point is blue or orange. So I think this one is the simplest one. This one is easy to figure out whether it's blue or orange. And here you can choose the inputs. Here by default you have the x coordinate and y coordinate. And here you can add more neurons or more layers and test how well the network guesses which points are blue and which points are orange. If we take a harder example here, you can see that the network initially doesn't learn very well. It thinks all the points are above this line are orange and all the points here are blue. But in time, as we go more and more epochs, it learns to classify them better. You can also try different variations. We have different nonlinear functions and all kind of knobs we can turn. So I think this is a really nice playground. Here you can find another tutorial on neural networks by 3Blue 1 Brown. He has a lot of nice animations to see how to guess which number is in an image. All right. And the last one is a free course on Coursera by Andrew Ng. It's really popular, even though it's quite old, but it contains the basics of machine learning, not only neural networks. I heard a lot of good things about this tutorial, this course. And it's also free. All right. And thank you for watching. I hope it's been a pleasant journey. Please drop a comment if you have any suggestions. And thanks to Bingo, my editor. I'm really good at making presentations. Thank you and have a good day. Bye.